I want to have a section of this course on symmetry for a few reasons. One is that symmetric functions, such as quadratics that look like parabolas, these are very common in economics. And so functions that have this form, we're going to see are symmetric functions. When a function is symmetric, we can exploit its symmetric properties to help us solve problems and check our solutions to make sure they're correct if we're using a different method to get to that solution. So for example, when we're in calculus, you can use calculus as we will in chapter 8 to find a max or a min, but you might want to double check that you found the correct max or min, and you can use symmetry and some of what we're going to talk about here to do that. It also is a nice way to practice applying math notation. And the reason why that's important is because I want you to get some practice reading the textbook and trying to have a better conceptual understanding of math. If you can read textbooks and have an idea what they're trying to tell you, that's going to make you a much better economics student. It's going to save you a lot of time when you're studying. So I want to try and show you how to do that, and I think this topic is sort of a gentle, fairly easy way to understand that. So hopefully by the end of this video, you'll be better at applying math notation and understanding abstract concepts in mathematics. Finally, previous students who've taken this course have found this section to be very helpful to them. So I asked students in the summer what topics they thought were really useful in Econ 1530, which were not so useful. And this one showed up as being, please don't take it out, useful. So hopefully you will also find this topic useful. Now there are different types of symmetric functions. There's two types. There are even functions, and even functions are the ones that I want to focus on today because I'm not, those are the ones that I think are most useful for an economist to know. I'm not so sure about the other type of symmetric function, which are odd functions. And so I'm just going to leave that to the side. In fact, I'm not going to talk so much about odd functions today. I even took out the slide. If you want to look it up in the textbook, you can see it. By definition, they're symmetric around the x-axis. And so I'm going to show you what at least what the even function looks like because those are the most useful. You can look in the textbook, look up the odd functions if you're curious. It's a good thing to keep in mind that most functions are neither even functions or odd functions. They're not symmetric at all. So a function does not have to be symmetric. Not all of them are symmetric. And an example of that is a linear equation. Now, what does symmetry look like on a diagram? Here is an even function, a symmetric function. That's symmetric. Now, let's just look at the graph. Don't look over there yet. What do we see when we look at this graph? Well, we see that y is equal to f of x, but also y is equal to negative f of x. So there are two x values with the same y value. Right? Remember when we were talking about one-to-one functions? To bring it back to that, is this a one-to-one function? No, it's not, right? A one-to-one function has one-to-one has only one y value for each x value. going to leave it misspelled because I think if I put in that E, it's going to go right down to the next line. So this is something about symmetric functions that you can take advantage of. In fact, in general notation, a function which is symmetric around the y-axis, has the property that f of x is equal to f of negative x. So this is one property that it has. It has another property too. Notice that if I asked you at what x value is the y value maximized? So looking at the graph, at what x value well, I guess I don't, is the, is the y value maximized? Well, there's the max, and it is going to occur at x is equal to 0. Whatever that maximum value is for y, it's occurring when x is equal to 0. The max occurs when x is equal to 0. Now that's not, that's only because it's symmetric around the y-axis. What's the real punchline here? Notice the max occurs at the midpoint of x and negative x. And so if I measured this distance and let's say it was 3, so that's basically saying x was equal to 3 and negative x was equal to negative 3, then the midpoint between those two values is 0. And so the max min is always at the midpoint between two x values with the same y value. So we can find the max or the min at the midpoint. Now, what if we have a symmetric function, but it's not symmetric around the axis? So it's symmetric around the y-axis. It's going to be symmetric around a certain point A. And so we've got A here. Point A is also the x value which maximizes or minimizes the y value. Now here's where I'm going to try to teach you how to read some notation, and it's a little confusing because of the x's. a function is symmetric around a point A if this equation holds. So if I plug in some numbers here, let's say that A is equal to 10, and I'll just say that x is equal to 2, so that we've got 12 here and we've got 8 here. Then if this function is symmetric around A, it must be the case that f of 10 plus 2 is equal to f of 10 minus 2. Or f of, oops, oh no, I did it right. F of 12 is equal to f of 8. And we can see that here, because if I said, oh, if I just said this is 28, these coordinates, 8 and 28, and 12 and 28. And so whether x is 12 or 8, it's going to give the same y value. This function is going to return the same y value. Now let's look at an example. We've got a function here, a quadratic function, and we're being asked to find the max or the min. And we remember from the assignment that we did earlier in the course, we had a question, and we should know here that if we've got a negative x squared, we're going to find a max, and the max or the min if we've got ax squared plus bx plus c, then the max or the min is going to occur at negative b over 2a. And here we've got a is equal to negative 1, and we've got b is equal to 8. So we're going to get negative 8 over negative 1 times 2, which is going to be equal to 4. And this 4 is our x value right here. And if I dot my way up to the top and dot my way over here, I'm going to find the maximum. Now you could have just looked at the diagram, told me what the maximum was. If I want the y value, and the max value is going to be equal to negative 4 squared, that's written like that, plus 8 times 4, and we're going to get 16. So we know at this point over here is 16.